And now our next speakers will also present about DNS tunneling, but using neural networks detection. So please, Dejan, Donin, and David Rodrigues, the stage is yours.
I'm Dejan, Donin.
Yeah, so I'm David, and I work at Cisco. I'm now a part of Talos. Dejan is a part of
Resolver team in Cisco, Vancouver, BC.
Yeah, and so this work is joint collaboration with lots of amazing people that we work with. So this talk will be in like two parts. There's two of us up here. So I'll just kind of briefly talk about what I will, and then Dejan will take over and give you a brief idea of what he will. So I'll be talking about this CNN architecture that we constructed that's called Pink-Lemur. Naming is hard, and be careful what you come up with because it gets stuck. So Pink-Lemur is kind of a spin-off of the idea of llama, and it's now ingrained in sand, it looks like. So, but yeah, so this is a CNN architecture that we've implemented and then deployed in our resolvers. I'll talk about this architecture, how it's using character embeddings and different optimizations or thoughts that we had to kind of wrestle with before deploying it, and then how we were able to train this model to detect exfiltration and DNS tunneling versus other DNS names that look like tunneling but are most likely benign. That kind of brought up this issue and why we went this way.
And I'll talk about the implementation challenges and implementing this on the resolver fleet, doing the classification in real time and in a fast and a scalable manner.
Okay, so with respect to this slide, it's kind of just some more details about various things that we could go into more detail if we had a little bit more time. But the idea here is just that there's lots of different things when you're looking at strings of DNS names that you can start to kind of unravel and to try to have these convolutional neural networks learn various encodings, as you kind of seen in previous presentations. And other kind of methods that don't use CNNs, such as perplexity or entropy measures that allow you to kind of measure the readability of a label in a DNS name. But yeah, so at a high level, what is going on here with our solution to DNS tunneling in real time? So the idea is that given a DNS query, the resolver is then going to kind of branch into two modes. One is detection and enforcement. And the enforcement should kind of flow, or what we wanted to do was preserve the current flow of a DNS resolution in our resolvers. So typically a query would come in from a client, and then we'd apply policy. This policy may immediately stop the query resolution, and therefore the response gets sent back to the client, and we don't do any work in the resolver. We don't go up to name servers, we don't check the cache. And then this, for DNS tunneling, we wanted to kind of make this kind of adhere to that idea. So we introduced a new cache in our resolver that kind of applies real-time policy or real-time updates from models that are kind of living side by side with the resolver as it's doing its typical resolution. And then the second part is just before we kind of send back a response to a client, there's another kind of cache sitting there in the resolver. This resolver is kind of being updated with statistics on and different measures that would identify behavioral characteristics that allow us to tune into tunneling attempts. Okay, so why a CNN? So a couple of years ago, we kind of talked about, we came here and we talked about what we were doing, and we were not using a CNN. And so there must have been some problems at that time that we weren't really talking about. And one of them is just really simple. The measure and the way that we were doing things back then was using a very simple idea, which was like this idea of perplexity and entropy, which is a hidden Markov model, which sounds great, but is actually very restricted in what it can do. It can only look at characters that are side by side in DNS names. And as you can imagine, as names get bigger or get more complex, there's lots of edge cases that these models may not be best at identifying. So the CNN would allow us this larger window of scanning of a DNS name and then identifying encodings such as hidden data in strings. So the CNN architecture that we kind of went forward with was kind of the one very small snippet of the popularized ResNet model that uses a bottleneck architecture in CNNs. And so we have a very simple character embedding layer, which is then convolved through 3 different layers of convolution. And essentially these kind of widen, then restrict, and then widen, which essentially kind of replicates a sort of autoencoder kind of architecture, which allows the model to kind of start to tease out various character learnings that might span various links between the label. And then the ending part of this model is just a simple binary classification in this case. I'm really not sure. Is there a timer here? It's at 15, and I have no idea how long I've been talking. But OK, maybe someone can update that timer so we know. Anyways, so once you get this model, then we have 2 training sets. And one of this was a historical training set from the last like 4 or 5 years of us running DNS tunneling detection offline, essentially what people would call batch mode. And while a clever algorithm in itself, it definitely has drawbacks because it essentially offline detects tunneling and then ships out domains to the global resolver fleet for detection. And there's obviously delays there and different situations that need to be addressed in more real time. And on top of that, we then came up with a secondary database. So that first data set that I just described is called our brew data set, and the second one is our signature data set, or signature DB data set. And this is essentially mock traffic that most likely this model would see. OK. So our kind of flow here is that we came up with an architecture. We have a training of this model on some various training sets. And then these model weights then get shipped to some storage location like S3. And then on top of this, we then have some automation that then picks up the latest model weights and then replays various traffic from, for example, that brew or that signature data set. And then, just like what's been popularized with LLMs, we have simple leaderboards where we just try to measure which model is best performing and in various categories. So the brew data set gives us a pretty good benchmark of like what we should be detecting based on our old standards. And then the signature data set would give us an idea of what we're about to see once we really deploy this in production. And so as you can see, there's like different model versions. These models are trained in various ways. They have different dimensions and character embedding layers. They have actually different training sets tied to each of them. Some of them might know about YouTube videos and their encoding. Some might know about JPEGs. Some might know about PDFs. And so we kind of play them all off each other, and we try to see which one is best performing.
OK. So this now remains the only remaining topic is the detail of implementation. So as I said, this has to run in real time on the resolver fleet, so it has many thousands of operations need to be executed on all the hosts. And also, as you may imagine, resolvers do way more than just this. They do the query resolutions, name server, delegation, and then policy applications per second. So everything has to be working kind of in a flow that is necessary for the query processing. So there can be thousands or tens of thousands of query resolutions, and this Pink-Lemur CNN calls in a second. Each query will have to kind of analyze the query, isolate the threat, flag it to the user, or block it if it's configured as such. So we had to do some clever processing to make it feasible. So starting with the first obvious thing to do is some kind of pre-filtering approach, so not all the queries go through this algorithm. First of all, we don't wish the free traffic, so non-customer traffic, to go through this DNS tunneling. So if somebody does not configure this threat detection, it will not go through this. So that will kind of cut down the traffic through it. And in addition, there are also some known exfiltration vectors which DNS can detect quickly. So those that are flagged with these faster algorithms are, again, not necessary to go through the CNN-based approach. And then there are also some domains that are on safe exclusion lists that, again, do not need to go through this classification because they are known to be not a threat. Okay, so this slide is a little bit wordy, but if you want, you can go back to it. It's probably easier to explain the operation and optimizations we've done in the next slide. So this is a real-time kind of capture of the flame graph, or like flame graph of the real-time processing of our queries. And you can see there is a marker there. Yeah, you can see there on the left there is a kit tensor con 1D operation. And I should say this flame graph was captured after the optimizations we've done. So this kit tensor conv 1D is the operation that takes the most of the time. So there's the convolutional 1D convolution operation that David just talked about within the CNN implementation. It turns out that when you port the PyTorch model into the C model, which we did, the straight port would end up with multiple nested loops, one inside each other. So that was one obvious bottleneck to optimize. It was taking way more time than this in the first version of it. So we attacked it first to make it faster. One obvious thing to do there was to kind of take a common part of these inside loops outside so that something can be pre-computed. So parameters that don't change in inside loops will be efficiently done ahead. So that's one thing. And another thing we've done there is that all these the data in the model is stored in tensors as a PyTorch model, so that these tensors also, we found it is more efficient, performant to encapsulate some other data ahead of the time and pre-calculated in these tensors, so that when they pass through these convolution operations and the binary classifier, in the end it goes faster. So that was done in part of this optimization. And in the end, so this flow shows what the resolver does in kind of regular operation. So it does this DNS tunneling first, and it does the query categorization, and then the query resolution at the end. So, and you have to have in mind these are the relative measurements and not absolute. But our goals of performing this within less than milliseconds and such was achieved with this optimization, so we were kind of satisfied. So this is now actually used on the fleet. Yeah. So yeah, in conclusion, what we've discussed here, this Pink-Lemur model, the CNN architecture, which is capable of detecting DNS tunneling in real time, and then to get to the solution, we experiment with different training sets, as David was saying, and we use different kind of models to do the trainings. We use these encodings seen in some common situations, such as in movies, in images and documents, to train the set and label the training set based on that. And its implementation itself was done in C, and the code is ported from the PyTorch model to achieve maximum efficiency. And bottleneck was shown to be this 1D convolution, which was optimized, as I mentioned, and ended up with a resolution that was like in the order of 1 millisecond, which was sufficient for our needs. In terms of the future work, there's always something else to extend. You can definitely optimize the CNN model itself, so use a better model suited. And pre-filtering can be also improved to kind of better sort out what queries need to be passed into this classification algorithm. And one more thing that is not on this slide is a benefit of the CNN approach is that all it needs to be reconfigured is to upload the new weights of this neural network classifier. So it's in our kind of store to improve this and be able to kind of online, quickly, real-time apply new training data that will kind of adapt to new threats that are discovered and quickly adapt to it. Okay, so that's about it. Thank you very much.
Questions, comments? We have some time for questions and comments. Please go ahead. State yourself and your affiliation, please.
Puneet Sood from Google Public DNS. So thanks for presenting this. I'm curious if you have deployed this to production, to customers, and what false positive and false negative rates you are seeing there?
Yeah, it has been deployed to customers. Well, the false positives, I'll let David speak.
Yeah, so it's in production. Customers have been seeing this model in its gory detail, I guess, since like late last year. The false positives, well, that's a tough one, right? So those are typically customer escalations. So we haven't been really getting customer escalations on this yet, so that's good. But that's because we're running it in a very restricted way right now, where it's very conservative. So yeah, that's also us meaningfully being, we're dialing this in, right? This is the first time we're literally in real time putting a convolutional neural network in production. So we're kind of slowly opening the filters, you know, so. I mean, I have a question for you all. Who else is doing something like this? And so my question to you is, in your resolvers?
So we do that in some of our products in our resolvers, but we're not sure if we're going to continue to do that, but we can take it offline.
Yeah, I feel like this could be like meaningful discussion. That would be fun to hear what other people are thinking.
Okay, so thank you very much, David. Dejan, thank you.
Thank you.